All right, continuing on in section 3.3 with the rational zero theorem, I want to talk about what our final goal is in this unit. I would like to be able to give you a big old long polynomial function and have you know how to graph it, have you to know how to get the zeros, all of those things. You can look at this, and we know a lot about the graph already. We know the y-intercept. We know the far left and far right behavior. We know how many bumps and bends. But do we know the x-intercepts? That's the hardest part. We know there's 5 of them. We know we can expect 5 of them. But how in the world are we going to find the zeros, also known as the x-intercepts? Well, this is what we're going to do. We're going to do a whole lot of synthetic division and see if we get zeros here. And if you get a 0 here, then you know, let's say that you put all these numbers into the synthetic division and you put a -5 on the outside and you get a 0 here. Doesn't that tell you that -5 is a 0, also known as an x-intercept? But it also tells you that x plus 5 is a factor, doesn't it? And you would have to do this 5 times until you found 5 of them. But the big question out there is, how do you know what numbers to start with to put on the outside of your division house? Aren't there infinitely many possibilities? You could try 20. You could try -8. You could try 56. You could try -0.5. There's infinitely many possibilities. This problem, if I asked you to find the zeros, could take you a week to find all 5 of them. There's got to be a way to reduce our pool of possibilities that gives us a hint of what numbers to try on the outside of our synthetic division house. And that's called the rational zero theorem. It's going to reduce our pool from infinitely many options for this number to try down to a usable number. Then we're going to do DesCartes' rule of signs after that, and that might sometimes, not always, reduce our pool even further, so that we know what numbers to try on the outside of the house first. All right, so let's take a look at the rational zero theorem and see how that helps to reduce our pool, at least a little bit. All right, given, this is scary, but all it says is given a big old polynomial function where you have x to a degree and then 1 degree less, and then you've got different coefficients, all of that. Let p equal a factor of the constant term. Consider both positive and negative factors. Okay, what does that mean? First of all, it's talking about the constant term. So we're looking at the first example, and let's go to our constant term, positive 20. What this little bullet point says is, I'm going to put a little p over that. It says, it's telling us, make a list of all the factors of 20. Make a list of all the numbers that go into 20 evenly, both positives and negatives. I always start with 1 because 1 goes into everything evenly, doesn't it? We're going to put plus or minus 1. And then I list them in partners, plus or minus 20, because 1 times 20 is 20. The only reason I list them in partners is it makes me not forget something. The next number that goes into 20 evenly is 2. Well, -2 also does, so plus or minus 2. And 2 goes in 10 times. I'm going to list them as partners because, like I said, it helps me to complete my list without forgetting something. 3 does not go into 20 evenly. 4 goes into 20 evenly 5 times. The next number after 4 is 5. 5 is already in my list, so we know our list is done. These are all the factors of 20. All right. The next bullet point says, let Q be a factor of the leading coefficient. Okay, we're going to look here, leading coefficient. And we're going to make a list of the factors of our leading coefficient. The factors of 4, plus or minus 1, plus or minus 4, plus or minus 2. 2 times 2 is 4. 3 doesn't go into it. We're done. These are the factors of 4, the numbers that go into 4 evenly. Then last but not least, it says, all possible combinations of P over Q are the possible zeros of P of X. All that's saying is, and I'll tell you what we find out, make a list of the p's over the q's. We're going to take each p and put it over each q. All right, follow along right here. I'm going to take this p and I'm going to put it over each of my q's, and then I'm going to take this p and put it over each of my q's. But be careful, that sounds like a lot more than it is. We're going to take 1 and put it over 1. We're going to get plus or minus 1. 1 over 1 is 1. 1 over 2 is plus or minus 1/2. 1 over 4 is plus or minus 1/4. I have put my 1 over all of my q's. I'm going to move over to the 2 and put the 2 over all of my q's. But watch, 2 over 1 is 2. 2 over 2 is 1. That's already in my list, so I don't have to list it a second time. 2 over 4 reduces to 1/2. It's already in my list. I don't have to list it a second time. So I'm finished with this p. I can move over to the next p and put it over each q. 4 over 1 is 4. 4 over 2 is 2. It's already in my list. I do not have to list it again. And 4 over 4 is 1. It's already in my list. I don't have to list it again. Move over to 5. 5 over 1 is 5. 5 over 2 is not in my list yet. Bummer. 5 over 4 is not in my list yet. Plus or minus 5 over 4. But that takes care of 5. Let's move over to 10. Putting 10 over each of my q's. 10 over 1 is 10. 10 divided by 2 is 5. Already listed. 10 over 4 reduces to 5 over 2. Already listed. 20 over 1 is 20. 20 over 2 is 10. Already listed. 20 over 4 is 5. Already listed. All right, if I asked you to find all the zeros of this, here's your list of the only possibilities that exist. So don't put 3 on the outside of your synthetic division house. It is a waste of time. 3 is not even a possible zero. This P over Q list is all of your possible zeros that exist. We have just taken our pool down from infinitely many possibilities to 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now 20, that's a lot of times to do synthetic division. I would hope you would find, we're looking for 3 zeros. I would hope you would find 3 of them before you would have to do all 20 synthetic division, but still, that's better than infinity, isn't it? So this problem has just gone from taking you a week to taking you maybe half an hour. We want to get it down even more, and DesCartes' rule of signs in a minute is going to help us get it down more. But let's do one more practice with the rational zero theorem. Okay, so if you're given this problem, you make a list of p's. P's are the factors of your constant. That's negative 12. Plus or minus 1, plus or minus 12. 2 goes into 12, 6 times. 3 goes into 12, 4 times. 4 goes into 12, but it's already in my list, so we know we're done. Those are the factors of 12. Q are the factors of my leading coefficient. I'm looking right here at a 1. The only factors of 1, it's my favorite. I love when Q is a 1. So does it make sense to you that my list of P's over Q's is going to be the same as my list of P's? Because I'm just going to take all my Q's and put them over 1. I'm sorry, take all my P's and put them over 1. So I'll get plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. What have you found? The only possible zeros that work for this. So if I asked you to find all 3 of them using synthetic division, you wouldn't try 5. Waste of time. You've just gone from infinitely many possibilities to 2, 4, 6, 8, 10, 12. 12. That's not that bad. Okay. Let's go to this problem right here. They've repeated it. And it asks you to find all the zeros. We're looking for 3 of them. To find the zeros, I'm going to do synthetic division, and I'm going to hope I get a 0 right here. Inside the house, I put coefficient of x to the third, coefficient of x squared, coefficient of x, constant. On the outside of my house, I only try numbers in this list because they're the only possible zeros. You know what I always try first? I always try 1. I always try 1 first. Bring it down. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. Negative 11 plus 3 is negative 8. 1 times negative 8 is negative 8. Uh-oh, 1 doesn't work. Bummer. So 1's out. You can try 2 if you want, you can try 3, but I'm going to just end the misery and tell you that, sometimes you try things and they don't work. Let's try negative 1. Drop, multiply, add, multiply, add, multiply. Now you see why I put a smiley face inside the 0, because when you find it, you are going to celebrate. All right, I'm going to tell you something very important right now. You do not have to do synthetic division all the more time to find the other 2. This is a 3rd degree polynomial. It's 3rd degree. Every time you do synthetic division, you go down a degree. This is a 2nd degree. This is my reduced polynomial. Its 2nd degree is a quadratic. We can go back to Unit 2 and we can find the other zeros by factoring, or by completing the square, or by using the quadratic formula. When you get down to 3 numbers here and a 0, you are down to a quadratic, and we can go to the old rules. This entire function can now be written as x plus 1. Do you see how I got that? There's a minus 1 on the outside, a negative 1 on the outside that gave us a 0. That means x plus 1 is a factor. That's called the factor theorem. And we can write it as the product of x plus 1 and the reduced polynomial. Remainder of 0, constant is 12. This goes with an x to the first. This goes with an x to the second. We're going to get x squared plus x minus 12. Are there factors of 12, negative 12, that give me a positive 1? Hallelujah, there are. We don't have to do any more synthetic division once we get down to a quadratic. There's the other one. Negative 4. There's the other one. Positive 3. So my zeros. This, congratulations, you just learned how to factor this. That doesn't follow our regular factoring pattern. It's 4 terms. You would have tried to group, and grouping doesn't work on this one, but we just figured out a way to factor it. And the zeros are negative 1, negative 4, and positive 3. Are all of those in my list up here? They sure are. It might have taken us a while to get the negative 4 and the positive 3, but we could have done synthetic division and found all 3 of them. Okay. That is kind of it for now for the rational zero theorem. We'll use it again today, but let's talk about DesCartes' rule of signs. We need to recall how to do something that is going to be required for DesCartes' rule of signs, and that is how to plug in negative x to a function. We did this with even odd functions. This is completely different, but we have plugged in negative x before. If you plug in a negative x everywhere that there is an x, what is the result? Well, right here, we're going to get a negative times a negative times a negative, which is a negative x to the third. right here, we're going to get a negative times a negative. Isn't this negative sign going to disappear? Poof. And give us a plus 2x squared. Right here, negative times a negative is going to give me a positive, and the minus 12 comes down. Okay, there's a trick, and you've probably already put 2 and 2 together and figured out this trick. If you plug a negative x when there's an odd exponent, your sign is going to change from the original problem to your p of negative x. If you plug in a negative x where your sign is, where your exponent is even, the negative's going to it's going to disappear, and you're going to maintain the same sign from the original problem to the p of negative x. This is to the first degree, so it changed sign. Odd degrees, your sign will change. Even degrees, your sign will stay the same. Okay, let's see what Descartes' rule of signs is and how to use this concept to try to reduce our pool even more. The rational zero theorem reduces our pool to possible zeros. Descartes' rule of signs will help us to know if we're going to try the positives first or the negatives first. Okay, first thing we do is we inspect p of x. That means you look at your original problem, and it says, I'm going to tell you this in easier language, count the sign changes from term to term. So from this term to this term, do you see I'm going from a positive term to a positive term? That's not a sign change. But from term 2 to term 3, I go from a positive term to a negative term. That's a sign change between term 2 and term 3. From term 3 to term 4, I go from a negative term to a positive term. That is not a sign change because you went from negative to negative. When you inspect and you count the number of sign changes, there is one sign change. So there will be one positive 0. The number of sign changes tells you how many zeros to expect that are positive or negative. All right, this second part of Descartes' rule of signs tells you to inspect p of negative x. All right, we just did this problem. I think this is the one we did on the previous page. And we got negative x to the third plus 2x squared plus 11x minus 12. All right, let's count sign changes. When you change p of x to p of negative x, right here, I go from a negative term to a positive term. That's a sign change. Term 2 to term 3 is positive to positive. That's no sign change. Term 3 to term 4 is a positive to a negative. That's a sign change. There are 2 sign changes. Now this is tough, guys, so just write it and I'll try to explain it as best I can in a minute. So there are 2 or 0 negative zeros. Why am I saying 2 or none of the negative zeros? Because up here what it says, that inspect p of negative x, the number of negative zeros is the number of times p of x changes signs or that number decreased by a multiple of 2. Same goes for the positive ones. But if I subtracted 2 from this, I would get a negative number of zeros, and we can't have that. So if you get 2 or larger, you need to subtract 2 for those possibilities. Now let's kind of try to make a little bit of sense of this. I think it's not going to all come together for you until a few minutes from now. But aren't we expecting 3 zeros? So knowing what we know, wouldn't you expect 1 to be positive and 2 to be negative? Okay, look, we did this problem. This is the problem we just did. We got 1 positive and we got 2 negative. So Descartes was right. But what does this 0 mean? We're going to get, by the end of the lesson, by the end of this unit, we're going to get where you could have 1 positive 0 and 2 imaginary zeros, which don't count as positive or negative. Let's not worry about that for right now. But that's why you have to include, you have to go down by 2, is because it is possible to get imaginary zeros. You know the thing with the I? Okay. All right, let's do another DesCartes rule of signs, and then let's bring this whole thing together. All right, the first thing you do, we're looking for the signs of our possible zeros. We count sign changes. Positive to positive. That is not a sign change. Positive to positive. Nope. Positive to positive. Nope. Positive to positive. Nope. Positive to positive. There are no sign changes. 0 sign changes. So you know what that tells me? There are no positive zeros. None of them are positive. So let's talk about that. Let's say I do the PQ thing, and I get my pool. Plus or minus 1, plus or minus 2, plus or minus, you know, you can throw out all the positives. Your pool's just cut in half. Because DesCartes tells us that none of your zeros are going to be positive. They're all going to be negative. Or imaginary. Let's do our P of negative x. All right, I'm going to use the trick. You ready for the trick? If I plug in a negative x here, there'll be 5 negative signs. Won't that make this term negative? If I plug in a negative x here, negative, 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 this term is going to stay positive. It doesn't change signs because all my negatives, poof, disappear. If I plug in a negative x here, that's 3 negative signs. This guy's going to change signs. If I plug in a negative x here, poof, negative times negative is positive, that's going to stay. If I plug in a negative x here, it's going to change the sign of the 6x, and my plus 2 will remain. All right, sign changes. Negative to positive, there's 1. Positive to negative, there's 1. Negative to positive, boom. Positive to negative, negative to positive. 5 sign changes. So, there will either be 5 negative, okay, that's higher than 2, we have to subtract 2, or 3. That's still higher than 2. We have to subtract 2 again. Or 1 negative. Zeros. So I'll either have 5 negative x-intercepts, or 3, or 1. So what are my options here? This original problem tells me there's 5 zeros. None are positive. Either all of them are negative, or 3 are negative and 2 are imaginary, or 1 is negative and 4 are imaginary. Those are our options. All right, let's put a big, giant bow on this lesson with pages 87 and 88 and see if you can't see where we're going and how all of this is going to help us. The process to find zeros given 1 0. I'm going to put a smiley face there. If they give you one of the zeros, they're telling you where to start. Okay, if they give you a 0, you're going to use synthetic division with that 0 that they give you to reduce the polynomial. Once you get down to a quadratic, we've talked about this, once you get down to a quadratic, you're going to use, I'm going to scratch out the because I always like you to use factoring first if it factors. Use factoring. Quadratic formula. Can I just write quad form? The square root theorem. I'm going to just write it like that, if that's okay with you guys. Or complete the square to find your last 2 zeros. Once all the zeros are found, you can write your polynomial as the product of the leading coefficient and its linear factors. Let's not worry about the note until we get there. I'll tell you what that means. Okay. Find the remaining zeros of this polynomial function given that 2 is a 0. Yay, they gave us that 2 is a 0, so they gave us where to start. How many zeros does this polynomial function have? 3, and they gave us 1. We're missing 2 of them. We're going to use synthetic division to reduce the polynomial. So we are going to make our synthetic division house. X to the third has a 1, x to the second has a 3, x to the first -6, my constant is -8. They told us that 2 is a 0. Yay, that will help us. We're going to go ahead and use their 0 to reduce this function down a degree. We draw, multiply, add, multiply, add, multiply, add. They did not lie, did they? If you got something besides the 0 here, they're a liar. Okay, I told you that every time you do synthetic division, it goes down a degree. So if you start with x to the third, we're down to x to the second. We're down to a quadratic. If you like to memorize things, if when you have 3 numbers and a 0, that's a quadratic. This is your constant, x to the first, x to the second. We can write this polynomial as x minus 2. Do you see where I got that? If 2 is a 0, x minus 2 is a factor. Times the reduced polynomial. That would be x squared plus 5x plus 4. When you get down to a quadratic, you can either factor, complete the square, quadratic point to find the last 2 zeros, but let's see if it factors. Are there factors of 4 that give me a 5? Hallelujah, 4 and 1, right? So our final answer factored is x plus 4, x minus 2, x plus 4, x plus 1. And my zeros are 2, -4, and -1. These will be my x-intercepts if I ask you to graph it. You found them, we're good. That's the hardest part because you can get the y-intercept, you can get the far left, but we need the x-intercepts if we're going to graph it. So if you're given a 0, you use it to reduce the polynomial. Let's do another one. Find the remaining zeros of this, given that 1/3 is a 0. Bummer. But it's not scary. If you're given a 0, we immediately do synthetic division using that 0. 3, -1, -6, and 2 are my coefficients and my constant. And everything's represented. We didn't have to put in a 0. We draw. Oh, we multiply. This would look like it was going to be harder than it was. 3 times a third is 1. We add. We multiply. Oh, anything times 0 is 0. We add. We multiply. Positive times a negative is a negative, and 1/3 of 6 is 2. That tells me that I can write f of x as x minus 1/3 times the reduced polynomial. This is going to be 3x squared minus 6. Do you see how I got that? Remainder, constant. X to the first term won't be there because we've got a 0. 3x squared. All right, once you're down to a quadratic, and we knew it was quadratic because this is to the third, so this goes down, this is to the second. So once it's quadratic, we're going to use a different way to solve for this. Okay, we've got this one right here. Do you see that 3? That's a GCF. Let's go ahead and pull out the 3. I'm going to bring it all the way to the front. All I did was factor out a 3. And I got, started out here, left me with x squared minus 2. Okay, If this times this equals 0, either this is 0 and x is 1/3, we've already got it, or this is 0. Let's go ahead and set it equal to 0. It doesn't factor, it's not a difference of squares, but we can use the square root principle, one that you maybe don't quite remember. Let's add 2 to both sides. Let's square root both sides. You can use the square root principle when there's no x to the first term. Maybe that will ring a bell. But don't forget, when you take the square root, you put that plus or minus. So this is the answer factored, but my zeros are 1/3, root 2, and negative root 2. So you're going to like the problems probably when they give you a 0 to start with. Because when they give you a 0, they're telling you what number to start with on the outside. But that doesn't make us use the rational zero theorem and DesCartes' rule of signs. Let's do page 88 where we have to, this is what we have been working towards. We have been working towards me giving you this problem and saying factor it and find me the zeros. But it's got 1, 2, 3, 4, 5 terms. We don't know how to factor something with 5 terms, but we do know we're looking for 4 zeros. Let's go find them. How do you do it? Step 1, you use the rational zero theorem to make a list of the possible zeros. I'll put in parentheses behind it, that's the P over Q thing. Step 1, if I just give you a polynomial function and say factor or find me the zeros, is you are going to do the rational zero theorem and make your list of possible zeros. Then you're going to use DesCartes' rule of signs to determine how many positive and how many negative rational zeros there are. Then you're going to use synthetic division and the factor theorem to find the possible zeros. Once your reduced polynomial is quadratic, use the appropriate method to solve for the last two. The appropriate method could be factoring. The appropriate method could be using quadratic formula. It depends on the problem. Then once all your zeros are found, you can write your polynomial as the product of the leading coefficient and its linear factors. Okay, let's see how we're going to go about doing this. Find all the zeros of this guy and write your polynomial as product of leading coefficient and its linear factors. Basically, that means find the zeros and then write this answer factored. Here we go. Rational zero theorem. Here's step 1. When you don't have any information at all and you don't know where to start. Rational zero theorem. P's are the factors of negative 6. That's plus or minus 1, plus or minus 6. 2 goes into 6 3 times. Then 3 goes into 6, but it's already in our list, so we're done. We're going to make a list of our Q's. Those are the factors of my leading coefficient. My leading coefficient is 1. The only thing that goes in is 1. My final answer for the rational zero theorem are my P's over my Q's. And we love it when Q is 1, because then it just is a repeat of my P's. All right, step 2 is DesCartes' rule of signs. DesCartes' rule of signs says, take your P of x, I'm going to rewrite it, x to the 4th minus 5x to the 3rd plus 5x squared plus 5x minus 6. I'm just rewriting it because it's easier for me to see down here. And your directions are to look at the original problem and count sign changes. All right, I have a positive to a negative. There's a sign change. I have a negative to a positive. There's a sign change. Positive to positive from term 3 to term 4, so no. From term 4 to term 5, I have a positive to a negative. There's a sign change. 3 sign changes. That tells me that there's 3 or 1, because you remember you have to subtract 2 until you get down to either 1 or 0. 3 or 1 positive zeros. Guys, how does that help us? Well, there's 4 zeros. And 3 of them, at least 1, we know for sure 1 is positive, but maybe as many as 3. I'd probably start looking for the positive ones. But let's take a look and see how many negative there could possibly be. We are going to plug in negative x. My first term is going to remain positive because when I plug in a negative x, that 4 is going to create a positive. My next term is going to change signs because the negative will take over and then you'll have this negative and this negative that will give you a positive. My 5x squared is not going to change signs. Right here, I am going to change signs and my negative 6 comes down. Sign changes. Positive to positive. Nope. Positive to positive. Nope. Positive to negative. Ooh, there's a sign change. Negative to negative. There is 1, negative, 0 for sure. We're not subtracting 2 because you'll be in the negatives. So there's 1, negative, 0. Absolutely for sure. Okay. That takes us through the rational zero theorem and DesCartes' rule of sign. This is when we start our synthetic division. And we start trying numbers and hoping that they work. Guys, here's a common mistake. Some people take these coefficients and bring them down here. That should be a negative x. Don't do that. Go back to the original problem. Do you see how easy it is to accidentally do that? We're going back to the original. I'm even going to come up here. A 1, negative 5, positive 5, positive 5, negative 6. Guys, I think I'm going to gamble. I know there's at least 1 positive. I think I'm going to gamble that there's 3 of them are positive. You know, so I think I'm going to start with the positives and see if I can find those. Let's start with positive 1 because that's where I always start. We drop. Multiply. Add. Multiply. Add. Multiply. Add. Multiply. I never get it on the first try. But I love it when that happens. I'm about to tell you probably the most important thing that I can tell you about this unit, and it's a very common mistake. You don't have to start synthetic division all over. Our goal is to get down to a quadratic. This is to the 4th degree. This then would be to the 3rd degree. We are going to continue our synthetic division off of the reduced polynomial because then my 3rd degree will get down to a 2nd degree. I'm going to say that one more time. Our goal is to get down to a quadratic. So if we start with a 4th degree and do synthetic division once, we go down to a 3rd degree. You may do synthetic division off of the reduced polynomial, and we're going to get down to a quadratic by this point. 4th degree, 3rd degree, 2nd degree, and we'll be done. Okay. Anybody have any suggestions for one they want to try? We found the 1 positive. There might be 2 more, but we definitely know there's a negative. Should we go see if we can find the negative one? Why not? How about we try negative 1? It doesn't matter what you try, guys. We drop. Multiply. Add. Multiply. Add. Multiply. Add. The chances that you'll get both of them in 2 tries are slim to none. But we did. And now this is quadratic. Yay, we got our quadratic. How do we wrap up this problem? we are going to write our p of x as, if 1 is a 0, then x minus 1 is a factor. If negative 1 is a 0, x plus 1 is a factor. And what we're left with down here is x squared minus 5x plus 6. Once you're quadratic, if it doesn't factor, you'll find the other zeros with the quadratic formula probably. And this would be your final answer factored, but this guy does factor. Yay. Our final answer is x minus 1, x plus 1, x minus 3, x minus 2. And my zeros are 1, negative 1, 3, and 2. These right here, these two things answer the question that's being asked. It asks you to find all the zeros, boom, and it asks you to write it in factored form, boom. Y'all just learned how to factor that hairy, crazy, ugly thing. It factors down to this. Yay. So this is what we've been working towards. We'll get some more practice with it on another day.